Last time we looked at our first conic section in detail, namely the circle, and that was a nice gentle introduction because we have thought a lot about circles before. Today we're going to be thinking about our second type, which is a generalization of the circle called an ellipse. Now, what is the textbook definition of a circle? Well, it is the points that are some given fixed distance away from the centre. We take that radius, that length, and we sweep out all of the points that are that distance away from the centre. Well, here's a question that's not really well formed, but what if a circle had two centres? So when we think about this, we're going to end up with what we call an ellipse. And an ellipse is the set of points, the sum of whose distances from two given points is constant. So our ellipse will look something like this, and that's because each point on this ellipse, when I measure this distance and that distance, so say distance 1 and distance 2, we want that sum to be constant. If we ask what points do we get, we sweep out an ellipse. So here at the top we see this definition of an ellipse. It's the set of points so that the sum of the distances from that point to two other points is constant. Now those two special points are called foci. Okay, that's the plural of focus. Each ellipse will have two foci. Now I've put a couple of links to videos in the video description that actually show somebody physically creating an ellipse using some push pins and some string. There's also a link to a little app that will let you play around and see how you can produce an ellipse. Of course, if you have your own push pins and string at home, go ahead, try it for yourselves. One of the videos is a little bit longer, but I liked it because the carpenter in that video used a lot of the language that we're about to set up when we talk about ellipses. So we're going to jump straight in with the standard form for an ellipse. To make a simplifying assumption, we're going to assume that we're centered on the origin. Okay, that makes our standard form a little bit nicer. We'll develop this further once we've seen some examples. So just like a circle has a constant associated with it, namely a radius, ellipses also have a couple of constants. So we have an a squared constant and a b squared constant. Those are just real numbers, and we're going to assume that the a squared constant is always larger than the b squared constant. Now, there are two different possibilities. Either our equation looks like x squared over a squared plus y squared over b squared equals 1, or we have this second possibility where the a squared and the b squareds swap. Remember, a squared is always the larger number, and that controls what type of ellipse we get. So if it's the x squared that has the larger number in the denominator, okay, because remember, it's always the a squared that is the larger constant. If it is the x squared that has the larger constant attached, we end up with a horizontally oriented ellipse. If it is the y squared term that has the larger constant in its denominator, we get a vertically oriented ellipse. Now this is easy to remember. We just need to think, okay, larger constant, x-axis horizontal ellipse, or larger constant attached to the y squared, y vertical. Okay. That's how we figure out which orientation we have. Let's see how these constants a and b affect the shape and size of our ellipse. We'll start by focusing with this horizontal example over here on the left. Now we always have two special points that we call vertices coming to us from that a value. In the horizontal case, we have a vertex at a comma 0 on the x-axis and a vertex at negative a comma 0 also on the x-axis. So a That gives us our vertex position. B gives you what we call the position of the co-vertices. Okay. In this case, because we're horizontally oriented, our co-vertices will be on the y-axis. We have one at position 0, b, and another at position 0, negative b. I like to think of the four vertices and co-vertices as being like the compass points of our ellipse. Now, the line segment between the two vertices is called the major axis, and the line segment between the co-vertices is called the minor axis. Now, which of those sounds larger, major or minor? Well, the major axis is going to be the larger one. It's the more important axis. It's longer than the minor axis. Finally, you can see these 2 points here and here, just like we had in this example over here. Those are the foci. Okay, we have a focus at the point C, 0 on the major axis, and the second focus at the point negative C, 0. Now notice there's no C involved in our equation for the ellipse, but if we do some geometry, we can figure out how C is related to A and B, and we'll talk about that shortly. Now, in our vertically oriented ellipse, it's all very analogous. You can see our vertices come to us from the A value, but this time they're along the y-axis, and the co-vertices come from our B values, but they're along the x-axis this time. And again, it is the longer line segment that we call the major axis. So this time, the major axis is vertical, and the minor axis is horizontal. And again, we have those 2 important foci points given to us on the y-axis this time. Now we have some information to record here, so let's get to it. We want to know the length of the major axis. Well, we're centered at the origin, and I can go a units to the right to get that vertex, or a units to the left to get that vertex. So the distance between them is going to be 2a. That's the length of our major axis. Similarly, the length of our minor axis is going to be 2b. The foci of the ellipse always lie on the major axis, c units from the center. So absolute value A, to summarize, is the distance from the center to a vertex. Absolute value B is the distance from the center to the co-vertex. And absolute value C is the distance from the center to a focus. Our picture's getting a little bit messy, but let's include it on there anyway. The distance from the center to the vertex is A. The distance from the center to the focus is C, at least in absolute value. And the distance to the co-vertex from the center is B. Let's think about the relationship between A, B, and C. Now it turns out C squared is equal to A squared minus B squared. That might look a little bit weird, right? It's not quite Pythagoras. If that negative was a plus, it would be the Pythagorean theorem. But here we get C squared as A squared minus B squared. Now I'll leave it as a challenge for you, if you're interested, to try and figure out why that's the case. It all comes down to making sure we have the correct pieces of string. So here, if we look at our ellipse, there's a couple of points that are relevant for us to be interested in here. There's this point. Okay, that's one of the co-vertices, right? So we could have our string pulled taut like that. And we also have this point here, one of the vertices, which is when we have our string pulled taut like this. Those two different points, if we make just the right measurement, we'll be able to cook up this equation here. So I'll leave that as a challenge for you. The super important thing is to remember this relationship so that we can apply it when we're dealing with ellipses. So let's see our first example here. We're being asked to write down the equation of the ellipse centered at the origin with co-vertex 2, 0 and vertex 0, 5, and we're also being asked to identify the values of a and b from the vertices. Well, first things first, let's throw down the information that we have. So we have a vertex at 0, 5, 1, 2, 3, 4, 5. There's one right there, a vertex, let's mark that with a v. We know there will also be another vertex at 0, negative 5. So there's our other vertex there. Co-vertex at 2, 0. Let's label that CV for co-vertex. We know there will be another one at negative 2, 0 because of the nice symmetry that our ellipse has. Okay, those are our compass points. Let's sketch in the rest of the ellipse. So you can see already, we can deduce that the ellipse is oriented vertically. So we know the situation is this right-hand guy up here. So our standard form is going to look like x squared over b squared plus y squared over a squared is equal to 1. So what are a and b here? Well, we have a is corresponding with the vertex. So a is going to be 5, b corresponds with the co-vertex, so b will be 2. So that tells us the equation for our ellipse in standard form is going to be x squared over 4 plus y squared over 25 is equal to 1. Now we weren't asked to find the focus points, but let's find them anyway, because we can, right? We know that c squared equals a squared minus b squared. A squared is 25, b squared is 4. So that tells us that c, if we take the positive square root, is going to be square root 21. So that's a little bit bigger than 4, a little bit less than 5. We know the focus points always lie on the major axis, so we'll have something like a focus there and there. Let's put F for focus. This next example is very similar, except this time we're going to be oriented horizontally, right? Because the vertex is at 5, 0. So we'll have another one at negative 5, 0. We have a co-vertex at 0, 2. We'll have another one at 0, negative 2. So we're oriented horizontally. We can read off that A is 5 from the vertex, B is 2 from the co-vertex. Because we're oriented horizontally, remember that happens when the larger a squared constant is in the denominator for the x squared. So our standard form will be x squared over a squared plus y squared over b squared is equal to 1. Substituting in, we'll get x squared over 25 plus y squared over 4 is equal to 1. Simple. As usual, we can put the cart before the horse and ask these problems the other way around. So in example 13, we're given the equation of an ellipse and we're asked to graph it and identify those important features, the center, the foci, the vertices, and the co-vertices. So let's look at part A together. So here, remember, a squared is always the larger constant that we see in the denominator. So since a squared is 49, that gives us that a is 7. We have, therefore, that b squared is the other constant, 16, and so b is 4. So that tells me, my vertices come from the A, but am I oriented horizontally or vertically? Well, the larger constant is attached to the x squared term in the denominator, so we'll expect to be oriented horizontally because of that. So we'll have a vertex at 7, 0, 1, 2, 3, 4, 5, 6, 7 vertex. We'll have another vertex at negative 7, 0. We'll have a co-vertex at 0, 4, and another one at 0, negative 4. Those are my co-vertices. Let's draw in the rest of the ellipse. We've been asked to also find the centre and the foci. So the foci come once we figure out what c is. Well, c squared is a squared minus b squared. That's 49 minus 16, 33. So we can take c to be the square root of 33. So let's fill in what we've been asked for. The orientation, we're horizontal. The centre is at 0, 0. We recognise that's our standard form for an ellipse centred at the origin. Our vertices are at 7, 0 and negative 7, 0. Co-vertices at 0, 4, 0, negative 4, and the foci, they're along the major axis, so the horizontal x-axis. We have these two foci at root 33, 0 and negative root 33, 0. So if we throw those on, root 33 is just a little less than 6, so we'll have a focus there and a focus there, F, F. For the second example, notice the larger constant is in the denominator of the y squared, so we'll be oriented vertically. Let's figure out what a and b are. So a squared is 12, that gives me that a is 2 root 3. That's a little less than 4. So we'll have 1, 2, 3, 4, something like there for one vertex, and 1, 2, 3, 4 there for our other vertex. What about b? Well, a little bit more straightforward. B squared is 9, so that means b is 3. So we'll have a co-vertex at 3, 0 and a co-vertex at negative 3, 0. Here's our ellipse. Let's throw down our information. So we know the centre, as before, is 0, 0. We have vertices at 0, 2 root 3 and 0, negative 2 root 3. Co-vertices at 3, 0, negative 3, 0. What about our foci? For those, we need to find c. Remember, c squared is a squared minus b squared. That's 12 minus 9. So c is root 3. That is a little less than 2. On the major axis, there's one focus. There's our other focus. So our foci are at 0 root 3 and 0 negative root 3. This next example is a little different in how the information is conveyed to us. So we're being asked to find the equation of an ellipse. We're told that we have a vertex at 3, 0, so there will have to be another vertex at negative 3, 0, because we are centered at the origin. And we're told this time where the focus is. So we have a focus at 1, 0, and so we'll have another focus at negative 1, 0. But we haven't been told anything about the co-vertices. That's okay though, because we can read off the vertex tells me that my a value is 3. Our focus tells us that c is 1, so we can use the relationship involving a, b, and c to figure out what b is and therefore where the foci are. So c squared is a squared minus b squared. We want to solve for b squared, so that's b squared equals a squared minus c squared. a squared is 9, c squared is 1, so that gives us 8, and so b is 2 root 2, which is of course a little less than 3. So we'll have a co-vertex around there, and a co-vertex around here, and we can complete our ellipse. Now we were asked for the equation of this ellipse, so we need to notice it's oriented horizontally, and so the larger constant, the a squared, will be in the denominator of the x squared term. So we get x squared over a squared, that's 9, plus y squared over b squared, that's 8, being equal to 1. Let's think now about how we can generalize what we just saw about an ellipse centered at the origin to working with an ellipse centered elsewhere, say at the point h, k. Well, to get from being centered at the origin to being centered at h, k, we're simply going to carry out a horizontal and vertical translation to our ellipse, right? We're going to translate horizontally by h units and translate vertically by k units. We know what effect such translations have to things like rules, namely x gets replaced with x minus h and y gets replaced with y minus k. So we're taking our original standard form centered at 0, 0, and we're just replacing x with x minus h, y with y minus k. Same deal with a and b, right? We're assuming that a is the larger constant, and for a horizontal ellipse, the a squared is in the denominator of the x term, and for a vertical ellipse, that a squared is in the denominator of the y term. So let's run through a couple examples here. It's very, very similar to what we were looking at before. We just need to make sure we're thinking about it in the correct way. Well, first things first, we've been given an equation here that is not in standard form. Right? Why is it not in standard form? Well, the right-hand side, although it's a constant, it's not the right constant. It's 100 instead of 1. So what we need to do is divide through by that 100. Oops. If we divide both sides by 100, that will give us x squared over 25 plus y squared over 4 is equal to 1. Aha! Now we're in standard form, and indeed the centre is even 0, 0. We're back in our original cases that we were looking at. So we can read off here, a is going to be 5, b is going to be 2, so we can figure out c squared is a squared minus b squared, that's 25 minus 4, therefore c is root 21. So we have our standard form already. That's what we were asked for. We got that simply by dividing through by 100, but now we can graph it. So we notice, because the a term, the a squared, is in the denominator of the x squared, we're oriented horizontally. So we'll have a vertex at 5, 0, and a vertex at negative 5, 0. We'll have a co-vertex at 0, 2, and 0, negative 2. And we'll have foci. Square root 21 is a little bit less than 5, but slightly bigger than 4. So we'll have a focus and a focus. So here is our beautiful ellipse. We were asked to find the vertices, co-vertices, and foci, so let's write them out. So our vertices were at 5, 0, and negative 5, 0. Our co-vertices were at 0, 2, 0, negative 2, and our foci were at root 21, 0, negative root 21, 0. Okay, this next example amps things up a bit. It's not in standard form. You can see it's not as nice as the previous example where we can make it look beautiful by dividing through by some constant. We're going to have to do a little bit of work here. Now, if you think back to what we did in similar examples when we were looking at our circles, we completed the square. So that's going to be our plan here. We're going to complete the square on the x terms, we'll complete the square on the y terms, and we'll see what that leaves behind. So, if we rewrite this just a touch, I'll gather the x terms and pull the common factor of 9 out. Do the same for the y's. So I'll gather, pull out a common factor of 4, and we'll have that negative 11 chilling by itself. We're now going to complete the square. So let's see how we do that. I've got 9. Going to complete the square inside that bracket. So I'll have x minus 1 all squared. Remember, that negative 2 coefficient is what I have to get that negative 1. But then I need to balance the scales and subtract 1 squared to make sure that I get the x squared minus 2x. Let's do the same thing for y. Going to complete the square, crucially inside that bracket. So I'll do y plus 2, all squared. Remember that 4 is going to have to give me that 2. Then I balance the scales. I need to subtract off 2 squared. And then we have minus 11, still chilling by itself. Now this does not seem super helpful, but it actually is. Okay. The next thing we want to do is, and hopefully this will make you see why, let's gather these constants that we can see are sort of muddled throughout. We can distribute the 9 and distribute the 4 to free things up a little bit. So when I distribute the 9, I get a negative 9. When I distribute the 4, I get a negative 16, and then I have that minus 11. Now what we end up with, when I gather, I get minus 36. Let's take that to the right hand side as a positive 36, and we'll divide through by that 36 now, because that will make us be in standard form. So the right hand side becomes a 1. My x term becomes x minus 1 squared over 4, and my y term becomes y plus 2 all squared over 9. So gosh, that was a lot of work, but at least we're now in standard form. So I'm going to erase some of this so that we can work a little bit more. If you need to go back and have a look, you can rewind the video. That's the beauty of this medium. But now we are at least in standard form. So what do we have? Well, we can read off a few things. First of all, the center is going to be 1 comma negative 2. Right? We have negative 1 plus 2. That means that h is 1 and k is negative 2. So let's throw that on our graph. Here is our center C. We know that we are going to be vertically oriented because the larger a squared value is in the denominator of the y term. And so we can read off that a is 3, b is 2, and we can calculate what c is. Except, oops, I've been a little sloppy and I used c here for center, so let's fix that. let's just write center is 1, -2. So here we can calculate that c squared is a squared minus b squared. That's 9 minus 4, which is 5. So c we can take to be the square root of 5. Now, we need to remember what A, B, and C represent here on the graph. They are distances from the center out to the various points, like the vertex, like the co-vertex, like the focus. Okay? So we know that we are vertically oriented. So if this is our center at 1, -2, my vertices should be vertically stacked if we're vertically oriented. So A being 3 tells me my vertices should be 3 units away from that center. So we should be 3 units up to get to one vertex. That's A, and 3 units down to get to our other vertex. So there's one vertex, and there's another vertex. What is tempting here is to say that the vertices are at 0, 3, 0, -3. That's what we were doing previously when our center was the origin 0, 0. Here, everything has shifted. So we need to make sure we're thinking about that correctly. A, B, and C here are distances away from that center point. So for the co-vertices, we know they are 2 units away in the horizontal direction. That's B and B. Co-vertex, co-vertex. And finally, where are our foci? Well, they're root 5 away, which is a little more than 2. So we'll have a focus there and a focus there. And we can now draw in our ellipse. Okay. So a little bit more involved here, because we had to first of all complete the square, but then also extract out A, B, and C and use those values correctly. So let's summarize. Our center was at 1, -2. Our vertices were, okay, we'll read them off. 1, 1, and 1, -5. Our co-vertices were at -1, -2, and 3, -2. And our foci, well, we started at that center, which was 1, -2, and we added, we moved in the horizontal direction. Our x-coordinate didn't change. We took -2 and we added on our c value of root 5 to get the upper focus, and to get the lower focus, we took -2 and we subtracted off our c value. Let's see another example where our center is not the origin. So here we have an equation. We're asked to graph the ellipse and identify the relevant points. Here, at least our squares are already completed, right? We don't have any stray x term that we have to somehow fold back into our squared bracket. That's been done for us already. So what we can do is divide through by that 1, 2, 2, 5. And that leaves us with x minus 4 all squared over 25 plus y minus 3 squared over 49 being equal to 1. So now we're in standard form. We can read off our information. First things first, we see the center is going to be 4, 3. So let's throw that on our graph, 4, 3. That's our center. Let's now figure out what A, B, and C are and correctly interpret them as distances in our graph. So are we going to be horizontally or vertically oriented? Well, the larger constant that I see, the 49, is attached to the y term. So we oriented vertically. So that tells us that if a squared is 49, a is going to be 7. So if I'm vertically oriented, to get my vertices, I'll start at the center, travel 7 units up, so that will get me to a y-coordinate of 10, and then I'll also travel 7 units down, that will give me a y-coordinate of -4. Those are my 2 vertices. Let's now find b. So if b squared is 25, that tells me that b is going to be 5. So to get my co-vertices, I'll travel horizontally away from the center by 5 units in both directions. So that will get me to 9, 3 for one co-vertex, and then it will get me to -1, 3 for my other co-vertex here. Okay, so we have our compass points, so we can at least draw in our ellipse. What are we missing? We're missing our foci, so we need to figure out what c is. Well, remember, c squared is a squared minus b squared. That's 49 minus 25, that's 24. So we can take c to be the square root of 24. That's a little bit less than 5, right? So to get our focus points, I need to start at the center. I'm oriented vertically, so I'll travel c units up by a little less than 5. So that will get me to a little less than 8. And I'll travel a little less than 5 units down vertically to get my other focus point. So let's record all this information. We've already got the center down. So for our vertex, we moved vertically. So the x coordinate of the center isn't changing. The y coordinate is, so I added a, which was 7, to get up to a y coordinate of 10. I subtracted a to get a y coordinate of -4. Those are my vertices. Similarly, for the co-vertices, it was the x-coordinate that changed this time. We added and subtracted b, which was 5, to get -1, 3, and 9, 3 as our co-vertices. And for our foci, again, that x-coordinate of 4 wasn't changing because we were traveling vertically. So we took 3 and added root 24, which we can simplify as 2 root 6, and I subtracted 2 root 6 to get the lower focus. This next problem again is presenting the information in a little bit of a different way. So we're told what our center is. It is 1, -2, and we're told that our vertex is 1, 4. 1, 4, and our focus is 1, 0. So we need to extract from this picture, this graph, what A, B, and C are. Well, A is always the distance from the center to the vertex. The distance here between these 2 points is 6. C is always the distance from the center to the focus. So we get that C is 2. And we can now use our classic relationship, c squared equals a squared minus b squared, to solve and find what b is. So b squared is a squared minus c squared, so that's going to be 36 minus 4, that is 32, which simplifies to 4 root 2. Which is around 5.7. So that means I can now figure out the distance from the centre to the co-vertex, it's a little less than 6 away horizontally. So I'll go 1, 2, 3, 4, 5, 6, not quite. 1, 2, 3, 4, 5, 6, not quite. So those are my co-vertices. I can add in my other vertex, which was down here, 1, 2, 3, 4, 5, 6, slightly off. And now we can draw our ellipse. We were asked to write the equation. This is a vertically oriented ellipse. So we get the centre gives us x minus 1 squared and y plus 2 squared. The vertical orientation tells me that a squared gets paired with the y term, so that's going to be a squared 36. B squared was 32, and that is equal to 1. Now something interesting that happens here is, notice this ellipse is fairly circular-like. It's not too stretched out of position like we sometimes see with ellipses. And that is an artifact of the fact that our a squared and our b squared are pretty close to each other in value. If they were perfectly equal to each other in value, say this guy was 36, I'd be able to multiply through by 36 and end up with standard form of the equation of a circle. So that's how the ellipse starts to get bent out of shape. When we start letting the A and the B differ more from each other, you get a more stretched out ellipse shape. Let's try another example together. So here we're asked to graph the ellipse with this particular equation. So we can read off the centre immediately is the point 2, negative 1. So there is our centre. Notice the larger constant, 16, is paired with the x term. So this is going to be horizontally oriented. We also get, that means that A is equal to 4 and B is equal to 3. That tells us our distances to travel away from the centre to get our vertices and co-vertices. So in our horizontally oriented ellipse, our major axis is horizontal, so our vertices will be 4 units to the right and 4 units to the left. So that gives me vertex, vertex. So my vertices will be 4, negative 1 and negative 2, negative 1. For our co-vertices, we're supposed to travel 3 units vertically away from the centre. So I get a co-vertex there and a co-vertex there. Those coordinates are 2, 2 and 2, negative 4. Finally, we're asked for the foci. We need to use c squared equals a squared minus b squared. That gives us 16 minus 9, that's 7. So c is root 7, that's a little less than 3. So we'll go 1, 2, 3, not quite, to get one focus, and then 1, 2, 3, not quite, to get our other focus. So in coordinates, we have 2 rather, minus root 7, negative 1, and 2 plus root 7, negative 1 for our foci. And now we can draw our ellipse. To wrap up our current discussion, let's talk about how we can graph ellipses on our calculator. It's very similar to the circle situation because, again, an ellipse fails the vertical line test, so it cannot be the graph of a function, but we can take an equation we're using to define our ellipse and solve for y, ultimately. So when we do this, we get 25y squared equals 225 minus 9x squared. If we divide through by 25 and then take the square root, this is what we end up with. But notice that plus or minus is what is making our ellipse fail the vertical line test. So we can take, in our calculator, a rule for y1 with the positive square root here, and we could take a second rule as the negative square root. That would give us the 2/2 of our ellipse, if that's y1 and that's y2. So, one last topic that we'll discuss today is the idea of the eccentricity of an ellipse and more generally of a conic section. Now, what do you think when you hear the word eccentric? If someone describes someone else as eccentric, what are they saying about them? They're kind of saying they're a bit weird. Okay. So if we accept as our gold standard of conic sections, if we accept that to be a circle, a nice, beautiful, perfectly round circle, okay, we say its eccentricity is 0. Now, E, the eccentricity of a conic section, can be any positive number or 0, and the larger that the eccentricity gets, the less circular our conic section is. Okay? So if we have an eccentricity that is small, close to 0, we get an ellipse. Okay? The closer the eccentricity is to 0, the closer the ellipse will look to a circle. As the eccentricity approaches 1, we get ellipses that are more and more stretched out. Okay? As the eccentricity approaches exactly 1, what we get is a parabola, which is one of our other conic sections. And when the eccentricity increases beyond 1, so say 2, we end up with a hyperbola. Okay. So the key takeaway, eccentricity 0 is a circle. Anything bigger than that is a little bit weirder than a circle. How weird, how eccentric? Well, look at the size of your value. So this table here summarizes everything I just said. For an ellipse, okay, you're going to calculate the eccentricity as c over a. So the distance to the focus from the center divided by the distance to the vertex. That's a formula we need to know and be able to compute with. What happens in the limit as the eccentricity gets larger and larger? Well, you get steeper and steeper looking hyperbolas. So something like this. And so what this diagram is trying to suggest is that as the eccentricity gets even larger, larger and larger and larger, your hyperbola starts to look like a line. So we think of a line as being something like an infinitely weird circle. Okay, the eccentricity is infinite. So at the top here are some more examples of eccentricities, thinking about how close they are to 0 or to 1, and thinking about how stretched out they look compared to a circle. This last example we'll see together. Let's have a look. So we have the center is 0, 0. We're going to be oriented vertically because the larger constant is attached to the y squared term. So that gives us that a is 5, b squared is 4, so that means that b is 2. So we can throw down our vertices and co-vertices. Being vertically oriented, I know that my vertex will be at 0, 5 and 0, negative 5. Our co-vertex will be, they'll be at 2, 0 and negative 2, 0. What's our focus? Well, c squared is a squared minus b squared. That's 25 minus 4, that's 21. So C is square root 21. That's a little bit less than 5. So we'll have our focus there and our focus there. Standard problem for us. But what about the eccentricity? Well, E, we do use the letter E to represent eccentricity. Okay, don't confuse it with Euler's number, E. But the formula for eccentricity is C over A. So that gives us root 21 over 5. That is roughly 0.92, which is pretty close to 1. It's not very close to 0. And we see we got a fairly stretched out ellipse. I wouldn't say this ellipse was very close to being a circle with eccentricity 0.